So how can we do this? We need to change our particle system and to add some more data to it, to the particles. So instead of using just a float-free type of data for particles, we need to declare a structure. Okay, we just create a structure for the particles in which we organize data in a different way. So we have float-free for position and float-free for velocity. And so we set this structure into the structure buffer that contains all the information for particles. Then we need to change inside the shader. Here, for example, we need to set that on reset the output position is taken from the reset position. Okay. Same here. Same here. It's okay. Okay. Now we need also a couple of changes because we changed the actual size of the buffer also, the stride. Because as Books told you yesterday, the stride is the actual dimension in byte, right? Yep. So now we passed from, we switched from 12 to 24 because we have also velocity now. So we need to double it. But
can you repeat what does stride mean? Because the book said that yesterday, but you can repeat what does it mean.
Stride is basically when you have a structure buffer, it's the size in bytes. So it's the size per element. So you have 1 bit, actually. Yeah. You have element count, which is the number of elements, and stride is the size of one element. So in that case, because you have like 2 for 3, it's 6 multiplied by 4.
Okay.
So, but as you can see, now we can't see the particles because we need also to change the forward shader because he expects to receive a float-free data for each particle, but now we are receiving we have a structure for each particle, so we can copy the particle structure here also into the raw particle shader. Okay. And replace the float tree with the particles structure. Then we need also to modify where we read this data. I guess it's this one. Yeah. The actual position of the particle is taken from the buffer, but just from the position of this structured buffer. Okay.
Can you show again the draw particles?
Yeah. I added the structure. So I replaced the structure in the structure buffer. Yeah. And then I added the information about what data I'm reading from that buffer. I'm reading the position of that structure. Okay. Yeah. If someone of you has some problems, just raise your hand. So, okay, Mr. Brooks can run to you. Okay,
Can you show both shapes?
Yeah. Any other problems?
Cazzo
serve tutte? Vabbè, va.
Bellissimo.
Ok.
Thank you.
So we added the velocity data to the particles, and now we can try to apply this simulation to the particles, the one I draw there. So we will let's modify the simulation computer shader, and let's say that on reset on line 24 we will also reset the velocity. Okay, so the particles, when will be resetted, they will stay where they are without velocity. Let's modify. So on, okay. Is there any problem? You just say, okay, on reset, velocity is equal 0.
What does VVIT refer to?
It's just the index of the particles into the buffer. So each time this operation is iterated, just give each particle has its index, so it can read the proper place in the buffer and apply the operation.
But it can be anything. The name.
Ah, yeah, the name, yeah, can be replaced. You can set here.
You can say that instead of flow free, you will use
Where?
for risking the velocity. You can say
Yeah.
instead of flow free.
Yeah. Okay. Then let's modify also the velocity cycle. So let's create a velocity variable. That's equal to the previous velocity value. So that's exactly like the frame delay somehow. Okay, so we are just reading the previous velocity. Then we can create a new pin for acceleration. So here in the patch, now we have also the acceleration 3D vector. Okay. So as we did there, we just use this acceleration added to the velocity cycle. And then we use these values from the velocity cycle into the position cycle.
Why do you have 2 rows of output post?
What?
Why do you have 2 rows of output post?
Here, no, I just added now, but I need to modify it. Yeah. So we read the previous velocity and we add the acceleration value to it. Okay. So this will be the new velocity in the current frame. And then we need to write this new velocity to the buffer. So we just write this value into the buffer channel of each particle. Okay.
So you need to use
It's really exactly the same as we have there, but we need also to we can do
here we can use vel instead of vel.
let's do it like this. Position, the new position is the previous position, okay, plus the velocity cycle here. Okay. It's exactly the same we did in patch there. So there is this velocity cycle, which is added after to the position. Okay, let's start to, you see, start to accelerate actually. If you zoom out now a bit, you will see the particles that accelerate. They don't move the same velocity anymore. Because actually velocity is increasing at the same speed each frame, but this value is added to the position. So each frame, the position will increase a bit more. So it's like an acceleration, so the velocity starts to increase. Okay. Yeah, usually in the particle simulation, we always multiply the velocity here, the velocity cycle, by a number that is almost 1, but it's not 1. So somehow we keep the velocity down. We avoid to increase the velocity much. So. So we are sure that velocity somehow is not increasing too much. We can call it damping. Let's create a new parameter called damp equal to the default. Let's put to 0.9 actually. Okay, and then we will multiply the previous velocity we are reading at the beginning of the complete shader. We multiply it by the damp. So each frame, before increase the velocity with the acceleration, we decrease it with just a little with this value. It's somehow the friction, the air friction of the world. Somehow it works like the same. Okay. So now, if you look at the particles now, they start to accelerate, but at some point they reach maximum velocity because the actual acceleration is there is the damp that is opposing this force to the acceleration. So at some point there are somehow two opposed equal vectors, so the velocity stays the same. Yeah, so we are now at the particle system samples 2 with the position and velocity cycle. Now we could add, for instance, a ground bounce, just to make a simulation of particles bouncing on the floor. So to do this, we can just how does it work? Let's say that the floor is at 0 in y. If any particles move under this side, somehow its direction, its movement direction is reflected. Okay, so it will be reflected. So let's do this. If position y is less than 0, take the velocity, there is a function, it's called reflect, that actually does exactly this thing, just reflect a vector.
-1, right?
Yeah?
Then multiply by -1.
Yeah, we could also just multiply the y component of the velocity by -1. But in this way, we will be able also to use, instead of a flat floor, we could, for example, use a terrain. So we, for each particles know where she is and can somehow know which is the normal of that in the point of the ground. So you can use that vector to actually really reflect this velocity correctly. Okay. So let's use this one. By float 3. We just gives now a fixed vector for the floor.
Missed floor 3 there.
Ah, yeah.
0. This one for the 0 is the center of the.
It's the center, yeah.
But as we start,
Ah, you mean there are particles beyond
the reset pose is at 0. The reset position of the particles are around 0.
Around 0. Yeah. We can actually, we need also to clamp somehow the particles. So we can also say that position y Okay, any problem?
Trying to make the y acceleration and then reset acceleration.
Yeah, they stop now.
Because we are starting from 0.
No, it's because just this one. This one. Let's just use this one. Yeah. Okay, let's add also another parameter called bounce equal to 1 by default. So we can decrease the force each time the particles actually bounce. Put 1 as default, but you can change it after. Okay, so if the position is minor than 0, position y, we reflect the velocity, then multiply the velocity y by the bounce value we just declared, and then we take the absolute position y, so we are sure that they're always major than 0 up the okay, if you try now, okay, they bounce. Is it working for you? Is it working for everyone? Okay, now they are continuing to bounce. So
Just one question. One understanding is why at this point velocity is not effect. If you change velocity right now.
you mean this one?
Yeah.
Probably it's not the net. No. Yeah, we are not using it anymore. You can use it if you want. You just add also this value to the position. So now you can also set a fixed velocity. Okay.
How comes when you increase the bounce, it still looks some kind of layery? There's
Yeah, I saw that. It's just because we are actually somehow clamping the position, I guess.
Right, because we're starting with a cube.
Yeah.
So the bottom and the top face that are, there is a phase between them.
that's what I mean.
Yeah.
If you increase the bounce value, it's even more clear.
The shader, you mean? Yeah, we can also somehow smooth this continuing bouncing of the particles, because they don't stop here. So we can create this bounce smoother. Just take the white space position, the space from 0 to 0.1, and use it to attenuate the gravity, the force. So if we just just open this.
Doesn't change a lot.
No. Use this. just open this one. Okay. I just opened the particle system 3 sample, so we can synchronize somehow. Okay, now we have the bounce on the floor. We can add also some. We can add an attractor, maybe.
Are we also supposed to leave that?
Yeah, we can just synchronize at the same pitch.
So this is the same as
Yeah, it's just the same, but it has also an attractor inside. So I want to show you now the attractor. Yeah. So.
Yes.
I need to disconnect. I don't know why, but probably didn't copy the texture. Yeah. You just need to disconnect the file texture from the forward pass here of the particles. Just delete it.
Select.
It's working now.
No, I select dot text.
Ah, okay, you can select. Yeah, but we will not use it. Okay.
How does it transfer takes that position? Just resolve.
How is the screen now?
Yes. I don't even see the particles.
Yeah, just. Okay. I made some changes in this patch. There is the bounce on the floor, we did just now. There is the attraction. In fact, you can play with the mouse in the screen, in the simulation. You see? And there is also this new channel here in the dynamic buffer, because I'm giving a random value for dump to each particles. because usually in particles always have some little difference in how they react to forces. So to simulate this, I just provide them a random value for them. In fact, inside the shader, inside the complete shader, in the velocity damping part, I don't use any given pin anymore. I just read the buffer W channel. Okay. Sorry? Is the fourth channel of this buffer, in which I wrote the position in X, Y, Z and random damping in W. Okay, it's this one. So I can give a random damping value to each particle, basically. Okay. Then the attractor. I just created a Boolean pin just to enable or disable the attractor, so we can connect it to the mouse. We need the position of the attractor, 3D position, the strength, and the radius. Okay, just a few simple parameters we found here. This is the position, the enable that I connected to the mouse, left, and then strength and radius. So what we do, basically, if attractor is enabled, I just take, I create this attractor vector, which will be the actual vector from the particles to the attractor. Okay. This is given by attractor position minus the actual position of the particles. So it's just a vector that connects each particle to the attractor. But I can't apply directly this one because in one frame each particle would reach the attractor, basically, because this is just really literally a vector with that point from the particles to the attractor. If I add this vector to the position in one frame, all the particles will be there. So I need to somehow reduce the length of this vector. And yeah, this I create this attractor force that gives you, basically, we want to control the radius of the attractor. So length gives the distance between each particles and the attractor. Okay, I divided it by the radius I give in the patch. So from 0 to 6 in this case is the distance. This distance will be mapped from 0 to 1. Okay. Then I do one minus attractor force, so we have maximum strength near the attractor and 0 at 6 of distance from the attractor. I saturate this force because otherwise we have negative also values. Then I apply a power function. It's like a gamma, so it's not really, it's decreasing not linearly but with a power 2 in this case.
Can you put 2.71 better.
2.71. Yeah, we have a mathematician.
You know the Nepero number?
No.
Euler.
Huh?
The Euler, the number of Euler of the Nepero.
Ah, yeah.
Can you explain?
It's a transcendental number that is found in nature. So if 2.71, 72, and blah blah blah, like B. But it's better for exponential. I don't remember the digit, but I think it's better for.
Okay. So, if the attractor is enabled, we just can evaluate this vector to the attractor and its force. So our velocity will be influenced also by this vector. So we'll take the original vector from the particles to the attractor. We will multiply it by the force we evaluated and by the attractor strength, which is the pin we created just to control manually somehow the force of the attractor. Okay. Any question? It's quite easy. Okay. So now we have one attractor, but we could maybe have multiple attractors. So what time is it? Okay, I will jump to the other and we'll explain you how to do it. Yeah. Serve la batteria, il caricatore. Ok. Arriva. Sì. Doesn't work.
Do you start it from the bottom or do you start from the lower?
No, from maybe from the higher. Okay, good point. Okay. Here we are. Now we have multiple attractors. How does it work? With multiple attractor, we need to evaluate the attraction for each particle to all the attractors. Okay. So we need a cycle, basically. This part will replace the previous attractor we did. So we use this function here to get the count, the number of attractor. Okay, wait. We need to create some buffers, structure buffer, to give the attractor data to the shader. Okay. All the information, the position, the radius, strength. So I created this buffer, a 3D buffer for the position, 2D for radius and strength. There they are. So I just create Berlin position for the attractors, and then I set the first slice with the mouse, so we can somehow control it. And then the same, I created this strength. So you see here, if we put negative strength in the attractor will repulse the particles instead of attracting them. In fact, the other attractors are pushing the particles away. Okay, so we have our buffers here with all the attractors data inside. This one. And okay, we will use now this information to actually create this attractor cycle. With this function getDimension, I get the count of from the attractor buffer, so I know how many attractor I have in the buffer. And then I create a loop. So for each particle, okay, I will evaluate this function for each of the attractor I have. Okay. So this is the count of the attractors, and then it's not that different from the previous samples. We will look at that. It's just we apply it to each attractor, basically. So it's really the same. We just, instead of reading the pins for the radius and strength, we read the data of each attractor from the buffer.
What's the dummy in there for?
What's the dummy?
GetDimension. It gives you an extra data that you don't need.
What's that?
I think I remember. We'll check for you in a second.
This get positions. Where is it defined, or is it already part of?
Where?
The get dimension. Sorry.
Yeah, this one is a function that
is already in it.
Yeah, in the sample, you mean the sample 4, 04.
Ah, in the sample 4.
Yeah. I just open it so we can move faster. So that's just a function that gives you the actual dimension of a buffer, by incoming buffer.
But how did you include it?
No. It's an intrinsic function.
It's already there. Yeah.
Mm-hmm.
So in this case, dimensions would be in the counter before.
Yeah, because it's reading. Just tell, okay, give me the position, the count of this buffer here, which is
like a slice count.
Yeah, it's like a slice count before. So if we increase here the number of attractors, it will be influenced by it. Okay. Then there's another thing I did in this sample. Basically in the forward shader, I use the velocity data of the particles as color. So just to give somehow a feedback of the direction of the particles. Okay. You can see if you enable the second technique in the shader. How I did it is pretty easy. If you go into the shader, basically I'm passing a vertex color from the vertex shader to the down to the pixel shader, okay, through the geometry shader. And in the vertex shader, I just read the data from velocity of the incoming particles buffer, and I'm mapping it just to fill the space of color from 0 to 1, so you can see the velocity somehow. Basically, I just created this Pico value, which is the color. It will be the color that I will take from the velocity and I will apply to the actual color of the particles. Okay. So I just here in the forward shader, I receive the whole information of the particles. So I receive the position, the velocity. I use the position to place the particles. And now I'm also using the velocity to give them the color. But since the velocity is a 3D vector, I'm mapping it in a way that the center of this vector will be 0.5 instead of 0. Otherwise, I will lose some of the direction. They will be black. So I just multiply it, the velocity, because I don't want to normalize. I also want to give the idea of the strength of the force. So I don't want to normalize it. And I translate it 0.5. So if the particles are still, they are gray. So they are, all the axes are 0.5. Then if they move in X, there will be a red component, and RGB are the colors for each axis. Okay. Just yeah.
Is it possible now all the particles the physics is on the plane?
Yeah, but that's just because of the gravity. If I disable the gravity, they start to.
No, I ask, is it possible that it will be not on the grid, or that it will be gravity, it will be toward the box or a different shape, different geometry?
If you want to, you have several ways to do it, which can come from the very simple to extremely complicated. But basically, for example, if you have a sphere, the collider is very easy to do as code. If otherwise, you can use distance field, but it's can be slightly more complex. But you can collide against geometry, for example. But the best is to have it as a volume. Like a collider against triangle is going to be way too slow. So if you have it as a volume, it will be fast enough.
Okay. Any question? Maybe we can have a break now. Just 10 minutes. 5-10 minutes. Yeah. Yeah, basically the mesh is quite it's not that easy to manipulate with the triangles. An easy way is to give some the actual position of the ground. So these particles know where is it X, Y, Z position. Sample the test I would not just in the high but also the normal. So you can create your normal. Then use it's not that easy, you just need to sample the test 3 different components and across operation you can get the normal. But I think there are still so each particle can sample that text and know if it's under that value it behaves constantly. Yeah, reflecting the velocity vector using the normal from the test. So it's a good product.
How would you try?
Not yeah, that's really easy. They usually do it's not that advanced like usually they don't collide with meshes, they just try to simplify.
And yeah, right. Imagine you have not triangles for a particle. Imagine you have your own mesh. Is it possible to input a mesh? Or you also have, you only have to do triangle strips to create one. I can input
No. You can instance. You just
instead of the null geometry.
Yeah,
I can instance
probably books after you will show. Will do some demonstration about. Basically, we are just creating a buffer with all the information.
Yeah, this is some kind of new stuff for me. I have to
you need to get in, but this is just spread with all the information, and you read it inside the shader. So you can read it inside. You can take a cube, instance it, and place it according to this incoming buffer.
Okay, I will try this right now. I will lower the particle count and try to implement a mesh, maybe a box or something.
You can try. You can try with this. He knows actually.
What's your experience like this dividing the particle movement and velocity by the time span?
I mean,
yeah, like it's very different frame rate. Yeah.
Nat, quanto vale? Un gettone,
the reflection.
Yeah, I have like a rope, for example, then fire the normal of this into the reflective lens.
If you have a landscape, you just provide the particle is beyond the ground level, but is that normal? We use it to reflect part of the
That's really nice.
yeah, they use it a lot for
That's called the law of refraction. That's present. I know the guy that invented this now. In physics, we study this. No, in physics, we study the law of Natan. Present or Natan? Present, okay. That's good, but only now. The law of la ley de Natan.
Yeah, can we continue maybe?
okay. Can we move on? Let's continue. No, I will open the next sample I did yesterday night. Just to show you a couple of new things. Is everyone okay? We continue? Yeah. Okay, I just opened the fifth sample. It's called Brownian Attractor Force Transform. Because the next sample, there's a couple of new things. One is Brownian. I called it like this because of the Brownian force. I don't know if you know what this. Electrons, particles, when they flow into wires, they don't move linearly. They have really chaotic movement, which they measure, which have really small component movement in one direction, but they move really randomly. Okay? So I try to simulate this random force that push the particles in any direction. And yeah, basically what I did is have a look inside the shader. I created a buffer, a structure buffer with basically a random direction for each particle. Okay, just to provide a big list of random directions. Then I create a float value just to control the amount of this random force. And then Brownian index shift. Now I will tell you that. Here in the simulation, this Brownian section control this force. So what I did is I used the index of the particle, of each particle, but I add this random shift to the index. Okay. The random shift is really a random number generated each frame. Okay. So basically, I'm just moving. This is my buffer. Okay. With all the indices of the particles. If I don't add this random value, it just go from 0 to 5 down, 500 down. Okay. But I add this random value, so they will move randomly. So the 0 should be 50, 46. Okay. Then, okay, so I translate the indices randomly, and then I wrap the indices into the same interval, because if I take the last particles, okay, the last indices, the last index, and I add a random value, this particle will have an index that is outside my buffer. Doesn't work. So I need to use a rat map. Okay. So there will my new indices will be wrapped, okay, in the same interval of indices. That's why I use this function mode here with the particles count. So I'm sure that whatever indices are generated, they always stay in the correct interval of the buffer. And then I use these new indices to sample the random direction, okay, from this buffer I created here outside. Just really a random spread that generate this vector really. So each frame, every particle will read a random direction, and I multiply it by my Brownian strength, so I can modulate it, and I add this random direction to the velocity cycle. Okay, so it's just a force that is applied to the particles. You can see here if I increase. Let me disable the gravity. If I increase the strength, you see the particles that somehow lose their shape. It's just a way of distributing them randomly.
Is that our galaxy?
No, the next one. In fact, if I enable the color, the color from the velocity, you see, they are all gray because they are still. But if I enable the strength, you see they are starting to move and color in randomly.
Excuse me. That main loop node needs to be at the magnet and not in gopro.
Yes. Usually, usually I do like this. I put this to 99 and I enable the vertical sync, because vertical sync is really nice. It's really make the difference on fluidity. I prefer this solution, but yeah, if your graphic card can't push 260 frames per second, it automatically jump to 30. Okay, so yeah, if you prefer, you can disable the vertical sync, and you will see the graphic card pushing higher. Bah, strange. Yeah, usually I use this kind of Brownian forces to somehow spread the particles, because if you, for example, use a 3D noise Berlin force field, the particles usually they go in the same point of the space. So if you want to keep them somehow separated, to spread them, I usually apply this random force to them. You see, if I disable the Brownian force and use the attractor, I create somehow there will be some parts of the simulation which are really dense. Well, it's just a new force. And then another thing is this attractor force transform. I made it simple here, but imagine we have the attractor. Okay? This is our particle, and this is the attractor. Okay? We evaluate the vector, the attractor. Before we just modulated this vector and applied a reductive version. Here instead, show the code. Yeah, this line. I'm modifying this vector, so I will rotate the vector of the attractor. So basically, you try to reach this point, but each frame I slightly move this vector, maybe this way. Okay. So the particle, instead of going directly through the attractor, move a bit in any direction. So from here, it will go here. Then evaluate again the distance, the direction to the attractor, but instead of going directly to it, it will move. It's just to give somehow, what you get is just a circular, a spiral movement through the target. Okay? Just a nice way to play with attractors. Here I just transformed this the attraction force with a transform. It's really not that optimized, but yeah, you can see here there is a rotate function. So if I disable it, now the particles go directly through the emitter to the attractor. Okay. What? You mean to differentiate for each particle? Yeah, you can do it. You just not using the transform now. Yeah, you could provide a buffer with the transforms, but usually it's better to use rotation functions. Okay, so in that case you can modulate these rotation values with a random buffer, for instance. So in that case you will get different rotation. So now they are going directly to the attractors. You can see if I start to rotate my vector, you see I rotate it in Y and I start to instead of going directly to the attractor, they continue to move around. They try to reach the attractor, but they always going in this spiral. Okay. Just a way to play around with these forces. And you can rotate also in the other axis. So you can also if I rotate too much my vector, okay. If I rotate it 0.25, I will get perpendicular vector, okay, because I rotated it like this. What does it mean? That the particles will move in an orbit around the attractor. Will never fall into it, or if I rotate 0.5, it will go in the other direction, for instance. Just think about these vectors as really, you can play with it, you can deform them. Yeah. Emitters. Let's try this simple emitter set. Ooh. Okay. Now, as you can see, there's quite a lot of difference. This was the shader for the simulation of the particles. Okay, the complete shader for the particle for the simulation. I created a new one for emission. Why? Because, for instance, in DirectX 9, we had to, as Brooks told yesterday, for emitting particles, we needed to write the whole texture, the entire texture, okay? So to read the entire texture and write just a few pixels, but always working with the entire buffer somehow of the particles. Now we have this scatter approach, so we can literally go and write just what we need in the buffer, the position in the buffer of the particles. So basically, I still keep my simulation shader here and create a new one, so just to keep separate. And while here I'm applying the simulation function to all the particles, okay, using the thread groups. Here I just call this function, this emit complete shader function, for the particles that needs to be emitted. Okay. So what I do, I decide the number of emitters. Now there are 4. Let me change. Julian, if I disable particle C,
yep.
I enable it. It will go to 60. But before was 30. I don't know why. And okay, I decided a number of emitters. And what's the final number of particles that I want to emit? Just I decide, okay, I have 4 emitters, and each emitter emits 30 particles per frame. So my final count will be 120 particles. So in my new emitter complete shader, I will provide the emitter position, emitter velocity, because maybe I want to emit a particle in a specific position, but also with a specific direction. Okay, like we see here, like this somehow fountain behavior. So I create this buffer, and yeah, I have an index offset because we are writing in our buffer. We are writing the meter particles one after the other. So we are little by little writing all the buffer. So we need to offset the indices, the current threads we are working on. So we need. I'm just using a counter here that just provides an offset using just increment this number each frame. Okay. So this number, this dispatch thread ID, gives me the iSpread ID from 0 to 120 now. But I use it. Where is it? Yeah. I add the offset, so I write all the particles, and then I use the same function we used before, the module, for keep these written indices inside my buffer. So this will be the index of the particles emitted. In fact, I'm using it to actually write the new velocity and position to them. Okay. I also provide the emitter count because maybe, like in this case, I have more emitted particles than emitters. So there will be many particles emitted from the same emitter. But my my dynamic buffer containing the information about the emitters is not big as the particles one, the emitted particles one. So I need to keep again the indices of the new particles inside the buffer of the emitters. That's why I do the same here. I just take the thread ID and keeps it into the emitter count interval. So if I have, like in this sample, 4 emitters, but I emit 100 of particles, they will read the buffer. The particles will be assigned just to the emitters, just to this buffer. So this particle will read the first emitter. Also these particles here. Also these particles here. They just read the same emitter.
So you actually don't add new particles, you just report the old ones?
Yeah, I just write the particles and not creating new particles. Just that's another story. It's books spoke about yesterday. There's a pen buffer. That's another kind of work with buffers. It's a dynamic count of buff, but yeah, they're used for particles, but I prefer to choose this approach because it's easier. It's better just to start with. So basically, yeah, now these particles are just getting the data from these two buffers, which gives the position and the velocity, and they are emitted this way. You see they are mostly green because the white is big. basically, I'm writing each frame, 120 particles are emitted.
Let's say they are jumping to the new bond position.
Yeah, they're just.
Lying in the plane.
Yeah, they're still. We have always the same number of particles. I'm just grabbing them one by one and writing to the emitter's position. Okay. It's really raw now as a particle system. You can scale the particles down. If you, for instance, if you put the lifetime tag into the particles, you can use it to modulate the size, for instance, and so you can. Okay. Also, seems that buffer is not good. I don't know why. Seems that buffer is not good.
Depth.
Right.
Put the state explicitly.
Small.
Depth sensor, yeah.
I already tried. Okay, here I modified a couple of things, so to let you see that, okay, previously we had just position and velocity in our buffer, but we can add more data, more values for each particles, and that's one of the biggest improvements for.
Is there a limit? How?
It's just about memory, I guess. Just because you need to increase the stride also, so it's just a matter of memory, actually. Yeah, you see here, I just added color and size. I'm not using size because I couldn't have time to do it, but I added color and size. Now, each particle will contain also the information of colors and whatever.
How do I know when I have to increase the stride?
The stride?
Yeah.
Yeah, basically, each float is 4, counts as 4. So you need to count, basically. 4 by 3, 4 by 9, actually, plus 4. So it gives 10. 4 by 10 is 40. So stride is 40 here. Keep in mind that if you change the structure here, you may have to change it also in the final shader, because it doesn't know which is the structure of the buffer. So if you don't provide the correct structure, you will mess up all the readings. Okay. In fact, you need to add also here the structure, the new data. And what I'm doing now, I just created a dynamic buffer, a color dynamic buffer, because I want to assign a color to the particles depending on the emitter. Okay. So I just created a dynamic buffer with colors for each emitter. This one. And in the emitting function, I just write position, velocity, but also color, okay, using this buffer. So now, on emitting, each particle will be assigned with a color. Now, the color is staying the same, actually, but you can modulate the color also during the simulation if you want. Then I just modified the forward pass here to read this data. And it's really easy. I just read the buffer, the color from the buffer, and I pass it to the vertex color I previously used for velocity. So here you can see you can manage different colors, assign to particles colors. And then I did another change. If you look at it, previously it was like this. The particles were emitted in a specific direction that was given by the velocity, the emission velocity. Okay, but maybe I want to, instead of having a single direction for emitter, I want to spread a bit that direction. Okay, so instead of having this straight line, I can have somehow a more spreaded emission. Also for this it's quite easy. I just use the same buffer I had here for random velocity, the one I used for Brownian. It's okay, it just gives me some random direction, some random values, so I just reuse it here in the emitter shader. This one. Of course, I need also an amount for this random emission. And okay, random emission velocity is I just read that those random direction and multiply them by the velocity amount. And basically I just add this random direction to my emitted velocity. So instead of going that direction, I will add this vector to a random one, so it will be slightly different. Okay.
How would we put a lifetime into the particle?
It's really easy. You can just I can use this one besides. Basically, there are many ways. You can just write the current time when the particles is emitted, and then after, where you need it, you can subtract the current time to this stored value, so you get the actual lifetime of the particles. Or you can, if you need to do this operation many times, you can also you can basically on emission you can set it to 0, this value, and then frame by frame you can increase it using the frame loop, the frame rate, because maybe it's going to change. So you get just the frame. You can use a stopwatch, for instance. Using a frame difference. This value gives you each frame what's the increasing lifetime. So if you add this value to each particles in the lifetime, you will get the lifetime increasing. Like you can use it wherever you want. Just so you can use it for scaling the size of the particles. So when they're born, they are 0 size, and then you can map this value using. You can use it for colors. I don't know. There are many.
So there is no GPU-based timing values, native GPU timing values.
It's all everything is GPU based here. It's just that. The only thing that tells the GPU that the particle is born is just the fact that I emit it. So no. This is not. This is just the interval I need to add to every particles. So it's just a value. It can be also static, but if the frame rate changes, maybe it's better to have an accurate value of how much time is passing by from a frame to the other. But everything is done in GPU anyway. You just add this single slice, look, like this. You just create a float, time step, okay. And each frame you can take now it's called size, but it can be lifetime, okay. You just let's go. You just add that value to every particle. So if a particle is when a particle is emitted, this value is resetted to 0. Okay, but
it's also a good idea to multiply the losses by time step. You're not bound.
Usually I didn't do it right now, but usually it's better to somehow create a relationship between the actual frame rate and the simulation. Otherwise, if the frame rate is changing a lot, also the simulation is changing. So you may, usually I use the timing from the timing node to get the actual frame rate, and use this value to actually multiply all the values like velocity and the others. So I'm sure that they always stay the same. The simulation behaves the same. Yeah. Nothing else here. Yeah. Okay. Take this.
Gonna explain a bit how also to do a bit more custom emitters, because for the moment we had static emitters, which is well, not ideal obviously. So I'll explain that. So you can use also, like if you want to emit your geometry, I'll show one example. So you have this node here, actually, if you wait for a second. You have this geometry node, which is async structured. So when you have a 3D model, normally it loads it as geometry, but geometry is not very handy to use in compute shader. So there's also this node which is async structured. So basically, you will have the position in one structured buffer instead. So that means you can load 3D model and use them directly in compute shader. So that allows you to, for example, generate, instead of having an emitter which is like just emit this particle, your emitter can be a 3D model by itself.
The position contains all the vertices coordinates or just one coordinate for the object?
Well, I show the shader code. So basically what you have is you have a position buffer, normals buffer, you have UV, and you have indices buffer. Indices buffer is a bit more tricky because it's not a structured buffer, but so you have in compute shader what you do is you have also this big buffer which is a little module which is called barycentric buffer. So it just generates a big random set of barycentric coordinates. So what you do, for example, here I put the sample also in. You take the position and the indices, so you technically you load your triangle, and depending on the size you emit a certain number of particles. So that's one of the ways to, for example, like you have a 3D model, you load any 3D model and you can just generate particles out of it. So that's one of the really handy emitting bits. And well, this one is a static morphing, so you have two models and it morphs from one to the other. One also useful trick is if you want to do shading, yeah, you have this line of code in your pixel shader when you do the rendering. So basically it's called pixel discarder. So if you want to render a circle, one of the very important bits is like if you render the full quad, the problem is if you want to render with depth because you want to apply shading in your particles, the discard trick is quite important.
Excuse me, so discard is a reserved keyword of shading language?
Yes, it's a keyword of shading. So basically,
it's just like a break?
It's different. Discard means completely discard this pixel. So that means this pixel will also not be written in the depth. So it's not going to be written as pixel, but also not more importantly, not written in the depth buffer. Because otherwise, if you put alpha to 0, the problem is you have a quad on the circle, which looks like a circle, but the problem is the whole quad is going to be written in your depth buffer, which is not desirable because you want it to look like a circle. Also, when you have your one other very handy trick, when you have your like lot of particle, you have this texture coordinates you bind into your geometry shader here. So that's the standard quad expansion. And here you have a texture sample. Yeah, basically what you do is you get rid of this text chord because it's just a hollow dot, it's just a circle. So what you do, you can also, instead of using a sampler, it's much faster to use you use a dot product instead to calculate a circle in the pixel shader. Like if you use, well, for a low amount of particle, like here it's okay, but when you start to do quite a decent amount, like over 5 million, you have quite a huge gain. Texture sampling becomes like a huge bottleneck. So that's how, for a model, that's how it works. So you have this big buffer, so you process. So you load basically the triangle. So you have like, you know, because it's an indexed buffer, you load all of the triangles. So you get your triangle, and from, like this one does, from the perimeter, it calculates a factor. So you say, for example, if my triangle is big, you want more particles. If your triangle is small, you don't want to emit a lot of particles. And you need to use, of course, append buffer, because you want to, you don't know how many particles you're going to generate at the beginning. So for people who so append buffer will deal that with you. It's a bit slow, but normally it's something you do only once, so it's fast enough. It's a very bad implementation.
Particles are applied to the surface. Particles are applied to the surface.
Technically, I load the model, but instead of loading the model in standard geometry, you load the model in compute shader, because technically your position buffer is just a buffer.
So can you also load particles from the volume of the geometry or on the surface?
Inside, I mean.
Yeah.
That's a bit more tricky. Well, the problem is like if, for example, if you use, if you know the geometry, like if you have a sphere, for example, you would not even need that because you generate a bulk of random number within a certain radius, and you have a sphere emitter inside. So you will not need, if you use a 3D model for it, it's totally inefficient. But the problem is when you have a 3D model, you have no information if you're inside the model or outside the model.
You can grab the normals and it's taking me really tricky.
Yes, but it's per triangle, so, well, you can do it in a less easy way, which is using distance field. If you want to generate particles also inside the model, the easiest is, well, the easiest, which is already hard, is to convert your 3D model into a volume texture. And if you have a volume texture, you know if the sign, it's a sign distance field. So that means if the distance from the point is positive, if you're outside the model. If the distance from the is negative, you're inside the model. So you could use that information, but it's quite already a bit more complicated.
Because I always use, like, when I want to do something like that, I always do it in Blender, for example.
Yeah.
Export the particle one by one, like in a list, and then load it.
If you export per vertex, but if you want to export inside the geometry randomly, it's quite a lot of processing, which is not very easy to apply. So, yeah, basically you just have to load some random points inside the triangle and you append them. So it's one other way to emit geometry. And I draw one which is texture based.
Excuse me, do you have the same number of particles for both models?
For which one, sorry?
Like you morph one model to another?
I try to keep the same model, yeah, in that case. It's not exactly the same, but it's a bit, I shape a tiny bit.
So you took just two models which look basically the same thing?
Yeah, you have tessellation factors. So normally I get a debug, which tells me the number of particles. So what I try to do is to keep approximately the same number. Like if it's 3 particles difference, it's not an issue. But if it's like a 10,000 particle difference, that becomes a very big difference. Yeah, there's another way to use it with texture. So, like for example, actually it's very easy with texture. So you can run your compute shader. You use app and texture exactly the same. That converts. You load the texture. You load the color, and depending, for example, this one just does a red channel. So if you hover the red channel, you emit a particle. And once you're done, you can, of course, animate it with this one. So you can, like, once you emit your geometry, you can write it to the buffer. So you can use append, or you can use offset table. So you're like kind of free to do it. But as soon as you want to emit a variable amount, append stays quite a good solution. Yeah, this one has a bit of specifics because it has actually no geometry input. So you can have shaders with no geometry. So yeah, you can use, when you want to emit now, because you have like a lot of information, you can use 3D texture, 2D texture, like, so you have a lot more possibilities also on how to, like, not only to animate your particles, but also on how to emit them as well. So that's about it for, yeah. Are you done? Okay, so yeah, about it, that's pretty much it. No, so yes, any more questions?
Could you just upload it to the buffer?
Sorry?
Could you just upload it to the buffer to
You can write to the buffer, but it's not necessary.
I mean,
No.
Which buffer? Yeah, I will copy some bits around here. Yeah, the big thing also, actually one very important bit is now because you're using compute shader and this drawing, you're not limited to the geometry anymore because you deal with the particles as it's just data, so which means you can render it as a quad, but you can also render it as a box, as a sphere, so a particle is not really this, like a lot of people think about particle as this static quad, but a box
can be
is also a particle, an object can be a particle. So,
Do you have an example with the instance in the particles?
Yeah, we could do it.
Just to add instance.
Just instancing.
I don't know if this one would launch. I have no idea if this is wrong. I think I will probably crush my graphics card like that. So I try to render 1 million sphere, which my laptop will obviously don't like. Well, box is obvious. Segment. I increase threshold a lot, so you don't have too many. So yeah, you can. So yeah, you're not bound anymore by what you want to render. You can also render a lot of different. So your particle can be quite anything. In that case, you render it as a segment. You can render it as a 3D box, so it's not.
Yeah, for instance, you can render as a box each particle and then use the velocity information to actually orientate this box. So it's like having a flocking behavior of these boxes.
Yeah, one big thing is if you use quad. One important thing, if you want to render a large amount of particle, don't use instancing with quad. Using geometry shader to extrude a point to a quad is much faster. Like instancing is good up to a certain level, but for over 1 million objects, it becomes quite slow. So geometry shader expansion is much faster in that case.
Question for the far future. I think at some point you will be able to particle interaction or real simulations, like through simulation. So each particle knows what the other is to interact with each other.
Oh,
come on!
Fun. Okay, neighborhood search. That's when things become fun. So, okay, so that ones are, well, to patch, you need to be able to write it in a custom plugin. Writing it as patching is just total hell. When I say hell, I mean hell. So yeah, if you do to do neighborhood search, you can do sorting on GPU. So I don't know if you're familiar with NVIDIA or Microsoft samples. So if you go on that's DirectX SDK, it's kind of old. If you go into sample browser, You should have this. Yeah, it's compute shader sort. So basically, if you want to have neighbor information, it's what the easiest way is you need to create a hash function. I don't know if you know about hashing. So you just need to give some kind of index, and then you need to sort these indices. So after, like, every neighbor will be next to each other. So it's not a trivial task. But yeah, GPU sorting, now you have quite some fast algorithm. I think this one is quite fast, but it's limited to 250,000. So you can't do more than 250,000. If you look into CUDA, I think they have a really fast 1 million sort, which is under a millisecond. But it's in CUDA, so if you want to port it into compute, you're more than welcome, because I didn't do it. But yeah, anything which involves neighbor involves either sorting or I forgot what technique I think it's histoparamid, but I really still don't understand how it works.
So we can stick to both 2D for the moment.
But yeah, you have other more advanced techniques which don't involve sorting, but it's more complicated. So.
Did you try to use some data structure?
Which one?
Did you try to use some data structure in whatever you're doing? I mean,
data structure.
Data structure. Yes, like I mean for positioning of the particles.
You mean from a model or?
No. I mean like for example, if you have to look at dynamics, is it the nearest neighbor search on the whole?
Yeah, that's why you use hashing. If you do a neighbor search on the whole structure, it's like on, I don't know how much this one is. Yeah, I think over 4,000 objects, your graphics, at least on the laptop, the graphics card will totally blow up already. So you need to use this acceleration structure. Without acceleration structure, it's going to be slow as hell. I think, yeah, 4,000 particle SPH brute force is already quite, it's 4,000 by 4,000, which is a lot. Yeah, exactly. So yeah, it's already 1.6 million iteration. So it's already quite slow. So if you want, and it's obviously n square algorithm. So it has, if you do 8,000, yeah, it's 64 million iterations per particle. So yeah, that's what.
What's inside the final boss for the new
What's inside it? Actually, I forgot what it was. Probably something not working, because if I remember, that was something I used for the Berlin demo in December. And that was supposed to be the last patch, but I switched to something else. Ah, no, that was actually, yeah, that was Spline. Yeah, I will see if I'm not sure it's gonna work, so no guarantee. Yeah, so it's yeah, it's just the splines system, so. So yeah, if you want some nice samples, actually the SPH one is explained here. Actually, it's coming from Microsoft. So if you want to look also on good resources, well, the Microsoft one is a bit outdated, but you have also NVIDIA. So if you look in, you have like a SDK from NVIDIA for DirectX 10 and DirectX 11, which both have nice samples on the DirectX 11 from Microsoft. So if you want to look for extra resources, it's they provide some quite nice samples for pretty much.
So we can install a DirectX SDK and NVIDIA SDK in any order without messing up?
No, they're totally independent. It's just a bulk of samples.
Okay.
So it's not even any driver or anything. It's just a set of examples. So you don't have any problem at all with that. So NVIDIA has some like really nice samples as well. And yeah.
But what about the new system with DirectX 11 ATI? Because that ATI is always like gonna change it.
Well, ATI don't have that many samples like built like this, but they haven't.
No, I mean just the new stuff that we've seen these days with DirectX 11. When I go back home on my desktop, what's gonna work?
On ATI, yeah. As long like, well, the good thing with DirectX is drivers are pretty consistent. So driver quality is quite good. So normally, because well, they use it for high-end games, which means generally it has to work on more or less every graphics card. Otherwise, your game will not work
properly.
But
then when you end up doing multi-screen stuff, you're gonna see difference.
Multi-screen works pretty much out of the box. Multi-graphics card, I need to change one line of code to enable it. For the moment, it's disabled. But it's there, but I didn't enable it in the build for the moment. But multi-screen is not a problem at all. So yeah, you can do the conclusion.
Other questions?
Many.
Ah! Yeah.
Because it's,
I remember.
Is it the same or it's the attractor for the particles?
No. That one was really easy. It was just a random position with the damping for each pitch. So they just trying to reach this random position. It was really, really easy. There was no flocking simulation, nothing like this. You could easily do it in GPU, also with the samples.
They have an example on the Microsoft one.
On the flocking?
Yeah, they have but actually I think it's how not to, like a few of the Microsoft sample is how not to do it, so you have to be a bit careful with it. And I think their board is a perfect example for that.
Oh yeah. Yeah, but this is quite advanced. I mean, this is a real flocking simulation, so.
Yeah, but it's slow.
It's slow.
So yeah, if you want to look on the voids, it's well, I think they use geometry shader because it's a DirectX 10 version. But yeah, if you want to look for extra documentation, you can you have quite a few good examples. Some are really nice, some are totally unreadable.
Basically, one could say all of the samples could be implemented in vvvv, or is there something where you have to program something as well?
Good question. A lot of them can be done pretty much directly. Some of them need to be written as plugin. It really depends on what example, but some of them are just like really like you start to look at the code and you just want to run away. But normally, technically, they could all be implemented by code anyway. But some of them are just simple shader, but some of them are just like a huge system, like the NVIDIA one have some really, really complex one, which is not like a straightforward thing to patch.
Like the fluid.
Like the fluid, the hair simulation, or interreflection. So, yeah, if you have the code, a few of them can be ported by code. That's what I did for a few of the samples, but they can all be done by code, but it's not like, some of them are really not a very trivial example.
Okay.
Can we conclude? Final word from Natan.
Yeah, thanks for watching. And
Yeah.